day of
Mr. Hooft is also in.
Mitra Memorial Lectures 2026. What we are gathered today here are for the last two sessions. Next slide, Alok.
Yeah, next slide, please.
Now, the Mitra Memorial Lectures, this is the second one. We had the first one in 2025, and it is our way to gather and pay respects and remembrances to Professor Mitra, who had larger than life influence on all of us, and very large and impactful influence on Indian science. And so we thought that it would be a just way of honoring him by holding these memorial lectures. Next slide. And nothing would please Professor Mitra than having a series of academic interactions at the very highest level. So we are very, very happy that Alok has put together this stellar show. In fact, stellar would be an understatement. And these wonderful 7 lectures. And today we are having 2, one by Professor Gerard Hooft on from the standard model to a renormalized quantum theory of black holes, and the second session by Professor Robert Wald on black holes, decohere, quantum superpositions. So it gives me great pleasure to welcome both the speakers, and added pleasure to me to welcome Professor Hooft, because I have known him for more than 40 years now. And we are extremely fortunate to have both of them, who are among the deepest and most original thinkers on this very, very important topic. Quantizing gravity has become the holy grail. And our 2 speakers today are renowned experts, not only on the gravitational side, but also on the quantum side. So it is going to be an intellectual extravaganza for us to listen to them this afternoon. But before we turn to that, we would like to take some time to remember and pay homage to some of our colleagues who are very closely associated with the Mitra Memorial Lectures, who passed away in the interim, and that's what I will do now. Alok, next slide. So I start with Professor Jaidev Anand, who passed away on 6th January this year. He got his MSc from Delhi University in 1959 and did his PhD also from Delhi University under the supervision of Professor Mitra in 1966. Later, he spent a major part of his life as a faculty member of Delhi University. His initial researches were in particle physics.
No, I don't hear.
Mostly in quark models and high-energy scattering. Next slide, please. Later, he worked extensively on neutron stars, quark matter, etc. His researches into compact stars, as well as quark matter, were extensive, covering such diverse topics as their behavior in intense magnetic fields, their bulk viscosity, stellar cooling through neutrino pair production, etc. Apart from these researches, he made it a primary goal to make technical matters as accessible to students as possible. Towards that, he published many books on special functions, group theory, waves and oscillations, etc., which were actually loved by students. He was a very dedicated academic and a loving, gentle soul who was very kind and warm to his younger colleagues in particular. His passing away early this year has left a void, and he will be dearly missed by all of us. Next slide. Next slide, Alok.
That's the next slide.
Yeah. Okay, thank you. Now I come on to Professor Naresh Dadich, who passed away very suddenly on 6th of November 2025. Naresh was born in 1944 in a Rajasthani village which did not even have a school. Through sheer determination, he went on to do his PhD in general relativity from Pune University under the guidance of the famous V.V. Narlikar, father of Jayant Narlikar. His dreams of a center for relativistic astrophysics at Pune became the blueprint for the Inter-University Center for Astronomy and Astrophysics, also called IUCA, which has emerged as a world-class center for university-based research, not only in astronomy and astrophysics, but also in cosmology and gravitation. It was jointly founded by Naresh Dadich, Ajit Kembavi, and Jayant Narlikar in 1988. He also served as the director of IUCA during 2003 to 2009. He was the president of the Indian Association for General Relativity and Gravitation. He was recipient of the prestigious Vaidya Rai Chaudhary Award of IAGRG in 2001. Next slide, Alok.
Yeah,
Here you see a picture of the founding members of IUCA, Professor Narlikar to the left, and Professor Dadich on the right, and Ajit Kembavi in the middle on the campus. This is a very, very beautiful campus. Those who have not been there yet should definitely make it a mission to be there. Now, apart from his extensive researches into general relativity, brain world cosmology, he played critical roles in India's participation in various telescope projects, apart from bringing gravitational wave detection to India under the ambitious LIGO India project, which is poised to play a very, very major role in coming researches on gravitational waves. He passed away very unexpectedly on 6th November last year while on an academic visit to China. We will miss his vision and leadership as well as his warmth as a wonderful human being. Next slide, Alok. Now we come to Dilip Chaudhary, a very, very close friend of mine. He passed away also November 2025. He too was born in a small Assamese village, but went on to become a leading expert on quarks and QCD. We were classmates in 1966-67 MSc batch of Delhi University. And since those days, we have remained very, very close friends. And soon after he
Hello, can you try to reconnect me? I heard something and I saw something in the beginning. Now I don't hear anything.
I can't. Sorry?
Sorry, I think Professor Hooft, this is Alok. I think, can you, I'm sorry, Professor Haridas, I think there is some inadvertent confusion here. So Professor Hooft, we can hear you actually. So right now, Haridas is in the middle of his presentation. So we'll get back to you at 4:50. I hope
4:50.
Yeah, I mean, I'll get back to Professor Hooft at around 4:50-ish. So yeah, I hope I was audible to Professor Hooft. I'm sorry, Professor Haridas. Kindly resume, please.
You are the boss.
Oh, no. Sorry. Yeah.
What do you
Please.
want me to do?
Yeah, please continue. Please continue. Professor Haridas, please continue. Please continue, Professor Haridas.
Should I continue?
Yes. Yes, please.
So we were talking about my dear friend Dilip, who was my classmate in MSc, and after that he obtained his PhD under the supervision of Professor Mitra on quark models, and quark models remained one of his major interests throughout his life. In 1971, he went to Oxford as an overseas fellow of the Royal Commission for the exhibition of 1851, and he started working with the well-known physicist Richard Dalitz. Next slide, please. In 1974, Dilip did a very important work on electron-positron annihilation into hadrons, which was published in Novocimento. In the paper, Dilip put bounds on a well-known parameter called the R parameter based on so-called broken conformal invariance. Many leading physicists of the time were working on this. For example, Parisi had predicted a value of 9. Dilip's predictions were right on target. Burton Richter, in his 1976 Nobel lecture, in Dilip's work among a list of other important works. And this was the time when there was not very much clarity about quark model. And this was one of the things that heralded the new world of asymptotic freedom, quark model, eventually leading to QCD. He was a recipient of the State Award for Lifetime Achievements. He authored a book just before he passed away called 50 Years of Quarks and Gluons, where he recalled many of his associations and works in the development of QCD and quarks and gluons. He was very active in promoting science in the Northeast. He was the founding vice president and president of the ANE, which is the Physics Academy of the Northeast. He contributed to spreading the physics culture in the Northeast with several writings in Assamese. He passed away unexpectedly, and all of us are going to miss him, not only for his many contributions, but his very friendly and warm nature. Finally, I come to Professor R. Ramanathan, who also passed away in 2025. He joined Delhi University in 1983 and retired in 2016. He was a man with varied interests. Quark gluon plasmas and stochastic quantum theories were among his major interests. He authored a book on stochastic quantum mechanics with Vasudevan and Pathasarathi. Next slide, please. In addition, he worked, something keeps closing my slides. Yeah, he worked on many frontier problems like proton decay, CP violations, Bethe-Salpeter equations, etc. He also proposed what he called interpolative quantum statistics. Another area to which he made important contributions is parastatistics in what has come to be recognized as Ramanathan-Haldane statistics. In an intriguing paper, Mitra and Ramanathan sought a dynamical bridge between classical mechanics and quantum mechanics by seeking to derive Liouville flows of classical theory from Wigner functions of quantum theory. The precise relation between quantum mechanics and classical mechanics has eluded proper understanding even to this day. Ramanathan was to present this at the last Mitra Memorial Lecture, but passed away most unexpectedly right as the Mitra Memorial Lectures had begun. His sudden loss has shocked all of us, and he will be dearly missed. Next slide, Alok. Now I want to mention Robert, popularly called Bob Sugar. He was not directly associated with Mitra Memorial lectures. He was my teacher at UC Santa Barbara when I was a graduate student. And while writing my latest book, Strings to Strings, I discovered an old Mitra connection with Bob Sugar. Bob Sugar passed away March this year. And this was a paper by Mitra, Gillespie, Sugar, and Nargis Panchapakation on the Fadé formalism to four-particle scattering. This was a paper which was 3 years before the famous Veneziano paper that opened the floodgates to the most recent developments. So with these offerings, now I request Alok Mishra to co-chair the next session, where Professor Hooft will be making his presentation. Thank you.
Thank you so much, Professor Haridas, for that lovely and touching homage to people we have lost this past year. Professor Hooft, am I audible to you? Professor Hooft, am I audible to you? I see he's unmuted for some reason. Hey, Professor Hooft, can you hear me? Let's see. I'm not sure what to do. Okay. Yeah. Not sure. Okay, let's see. For me, say something. Sorry. See, we are not audible to him. That is why he said to him. Yeah, actually, he might be facing some connectivity issues about which he had forewarned me in some sense, which is the reason why he said he'll be trying to connect 45 minutes in advance, as I mentioned earlier. But we, of course, see him. I don't know what to do. I see. I see. I don't know what to do. Send a chat message to him. Yeah, let's try that. Hope that works. I've just texted, sent a chat text to Professor Hooft. Okay, So we're slightly better off now. I see a blur. Let's see. See if there's an email.
So if we're connecting Google Meet, we can ship them back using Google. That's what she wants in this chat.
I just got an email from Professor Toft, which basically said that he could hear some sound, but when he wanted to hear better, he could hear nothing. And so I've just written to him saying that we see that he's unmuted. We see that his video is on. We're getting a frozen blurred image. If you would like to disconnect and reconnect, I don't know what else to do. I think he's most likely in a relatively remote place with some connectivity issues. I don't know. Are we getting something? So Toft, can you hear me by any chance? I can hear somebody typing. Maybe it's. Can you send an email? Yeah, I just did. Indranil. I just emailed him what I just said that I did. Yeah. I just emailed him. The problem is I don't know what the. Okay. See a reply. I don't know how to do these things. Oh man. How do I disconnect and reconnect? Oh, okay. Let's see. Okay, so how do I? Okay. Right.
Can you hear me now? Can you hear me now?
Yeah, yes, Professor Toft, we can hear you, definitely.
I cannot hear you.
Shoot. We can hear you. We can so hear you.
It's always like this.
Hello.
Can you hear me?
Yes, yeah, very much. Hello.
I cannot hear you.
What do we do?
And of course, I don't see my slides yet.
I have written to him. I've just emailed him.
I could
Saying-
start the talk if I can have my see my slides.
Okay. 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 I mean, okay. This is
I
something
don't
want.
understand why I cannot hear you.
Do you see your slides? I don't know. Well, you're not able to hear me. I don't know what to do.
Oh yes, now I see my slides. Very good.
Okay. Shoot. I just unshared. Okay. I'll send it to you. Okay. Yeah. Okay. Let me do that. Let me do that. Yeah. Right.
Yes, it is difficult to talk if I cannot see who is hearing me. So I'd like to get some indication that you can hear me. Shall I start the talk? Just nod if you say yes. Well, let me then just start my talk, okay?
Oh, hello.
Good.
Professor Toft, can you hear me by any remotest stroke of luck?
So
No.
to begin, I'm very happy to have been invited to give this talk. I saw that Professor Mitra has a same general view on science as I have, so it's certainly very interesting to connect in that way and to hear of his contemporaries. What I would like to do is to explain a little bit my view on how to do science, because I think that in the last decades a new trend has been followed where people think of the most fantastic theories and ideas and try them one by one, of course, to discover that they don't work. The fantastic theories don't work. What you have to do in science, to my opinion, is the extreme opposite. It is that we have to try to find areas in science where our understanding is best, and then see how we can connect different fields of our science to connect them together in one big frame. Think of James Maxwell, and when he thought of electromagnetism, the idea that electricity and magnetism are different sides of the same coin was very important, much more important than perhaps discovering a new term in the equation. But just to see how different fields of science connect together is the most important ingredient. And I have numerous examples of where exactly this happened. If you can give me the next slide, that is, slide number 2. Are the slides visible, by the way? Can you nod? Do I have slide 2 on now? Here it is. Yes.
Pata nahi yaar.
So it's the history of science that shows new theoretical constructions by combining theories that were thought to apply to very different fields together. So the Maxwell's equations, I brought those forward as a fundamental example. And I'll like to refer to that as the Einsteinian principle. Why Einstein? Well, this is exactly what Einstein did in his younger years, when he was very unexpectedly successful in answering some very basic questions where theories were not yet so well developed. Think of relativity theory. How do you set up relativity theory, and can you understand what the role is of the velocity of light when you're looking at very fast events? And he discovered that we have to be able to make transformations from one coordinate frame to another coordinate frame that is co-moving with whatever object you are studying. And that way you really discover new things. And that was the big surprise. The big surprise was that asking simple questions, but asking them in a very general way, would lead to very fundamental new answers. That holds for special relativity, but also holds even more for general relativity. So the idea is that this is the way we should continue our search towards better understanding of physics. And even though it is also clear that sometimes it's not the best solution. Every now and then we are asking the wrong questions or asking very relevant questions which turn out not to bring us very much progress. That, of course, happens also. But I see more often hundreds and thousands of papers on the archives where people dismiss all known physics and start from fresh, from doing nothing. That, I think, is not going to work. And the one example that I want to tell you much more about is black holes. In particular, the way how to connect black holes with the laws of physics, in particular where quantum mechanics is concerned. Well, this at least is understood by many researchers, that learning how quantum mechanics applies to black holes will be a very important approach to understand more physics. But then again, too soon, they drop all we know and start with crazy ideas, which definitely are wrong from my perspective. So we should be very careful in doing that. Rather, we should think of black holes in a very special way. And one of the things that we see happening in the case of black holes is that there's something very strange going on with information. Whereas information is also playing a central role in quantum mechanics. And also it plays an essential role in thermodynamics. So we should try to combine thermodynamics, quantum mechanics, and general relativity in one scheme, see whether sets of equations originally valid for one particular field turn out to be also extremely important for the other fields. In the case of black holes, by the way, we have seen this thing. We did see that the laws of thermodynamics with the differential equations certainly also in an unexpected way apply to black holes as well. The black hole horizon is linked to the black hole entropy. That not only holds for thermodynamics, but it holds very general in many branches of physics. Even in quantum mechanics, probabilities are very important. The probabilistic equations are central in quantum mechanics, but people don't realize that you should write the same equations for very many different fields. Also for black holes, large, small, you name it. There are also these particular approaches will be very successful if we do them more carefully. And that's the other big issue in making progress in science. I think lots of progress comes when someone says, we understood this, you understood that, but there's something missing in our logic. Something has to be done better. We are not saying that any of the laws we know are wrong. Quite to the contrary, we think the laws that we know are nearly perfect, but just not quite. We should see if we can add another brick to this edifice called science, and then see if we can connect all these different parts of our field together in one fundamental theory. And in the case of black holes, I've been following this path, but rather surprisingly, only very few people were following me. Now, please go to slide 3. So this is already what I have said for a large part. We have theories of black holes, but very often, until now, the questions about information in a black hole has been put as a side issue. Black holes are something special, and it looks as if we are making a step backwards if we try to get all that part right. Because the beauty of quantum mechanics is that you have to deny that true information is passed on, but sometimes there's a question of entanglement, and then multiple aspects of information are being dragged along in the equations, but not in a way that seems to be logical in the ordinary day of life. Personally, I think that conclusion was premature. Many of us have been involved with the development of quantum mechanics and tried to improve our formalisms. And very often this led to some sort of successes, but the idea that information is being transported in an anomalous way, in an illogical way, as it seems by the equations, to me this means that we have not been accurate enough. If you are very accurate, you discover, quite to your surprise, that laws of nature that we thought we knew very well actually have to be rephrased in very different ways. That holds for quantum mechanics. It also holds for general relativity and thermodynamics even. Of course, thermodynamics was before quantum mechanics. It became very well described, but actually I think thermodynamics is more intimately linked with quantum mechanics than people often realize. For instance, a particle is a point-like object. It has no dimensions, no space-like structures. It's just a point. You can do that in thermodynamics just as easily as in other branches of science and in quantum mechanics and in particle physics. But people haven't really very well taken care of the fact that this is a very fundamental phenomenon. So that quantum mechanics is very deeply rooted in many branches of science. Of course, that is the reason why quantum mechanics is so popular and being studied with such intensive force that, of course, quantum mechanics is having a very special position now in our view of science, in spite of the fact that I don't believe we have done it totally correctly. I think there are things missing in our present views of quantum mechanics. I'll say something about that at the end of my talk, because what I wanted to talk about was findings I have about Hawking radiation. Hawking radiation is a thermodynamical phenomenon because it tells you that black holes have a temperature, and so so temperature on one hand and thermodynamics on the other are very, and general relativity at the other, are very intimately linked, and that's where we should try to rephrase things better. And I've written some papers and met with lots of disbelief. Quantum mechanics was thought to be a fundamental mystery, something that could never be made up if you hadn't seen it happening in the experiments. I don't think that's the correct way of approaching quantum mechanics. There's nothing mysterious about it. The only mysterious thing is that quantum mechanics applies when lots and lots of parts are interacting. When you have a vessel with a gas in it, a large box with particles, billions and billions of particles, how many probable configurations are there? Those numbers are very difficult to discuss in physics because they are so large. So quantum mechanics is what happens when you work with very large numbers. Few people look at it that way, but I do. And I think you can make progress there. I'll mention something about it in the end of this talk, because I really wanted to talk about quantum mechanics and the progress we can make there, because that is something that is moving around. Quantum mechanics of black holes is making important changes in our views, but not drastic enough and not fundamental, better than what we usually see. Yeah, I'm now at slide number 5. If you can switch on slide number 5, thank you. Then we have to start from scratch with the case of black holes, and we start just with the Schwarzschild equation, which is a very basic fundamental equation for the most symmetrical black hole, the easiest one. The easiest black hole is described by this expression, which describes the metric surrounding a black hole, and outside and inside, where omega, the Greek omega, stands for the two letters theta and phi, the angular parts of the description of the metric, and d omega is a differentiation that you have to look at, and so you get the so-called Schwarzschild equation for the black hole, very central in everything we want to describe. Now, the Schwarzschild equation has also a limitation in it, which is it only applies directly if nothing is moving. So if you take your space and time stationary, then you can get this solution. Actually, the solution was obtained and also assuming circle symmetry, but that on the side. But there shouldn't be any other particles coming in its neighborhood, because then they cause curvature of space-time, and space-time curvature might possibly do harm to the solution. It makes the solution different. It was rather surprising, however, when people like Stephen Hawking and Penrose and others found out that even if you do put extra particles near a black hole, actually the changes are very light, very minor. The basic structure of this equation stands even if you do allow particles to fall in, or even if you allow several black holes of different sizes just collapse like this. Then even then you still have these equations. Can you go to slide 6? However, there's something important about black holes, and again, that important thing is being used by many scientists, but not enough. It is that when you look at the metric just describes only one square in this picture here. In that sphere, the Schwarzschild expression is exactly valid, but you can extend it analytically. Now, this is nothing new. We know that in mathematics, very often you have a solution to equations. You can look at what do the equations do when you apply them in a circumstance where things look very different. And that's here with the Schwarzschild black hole. It is it turns out to turn into two squares, not one, when you extend it analytically. And if you look carefully, you find that those squares are separated from each other by what we call horizons. So there are two horizons shown here, two black lines in this position. Those are the horizons of a black hole. A particle can travel through as these gray arrows show. The gray arrows show that a particle can move away from the region where the Schwarzschild equation was valid into another region. I call that region here the region 3, because region 4 and region 2 are the other two here. And you can discover that in principle you can try to solve the equations and see what those particles do after they cross the horizon. And many people ask this question and then think that you get new physics, but actually you have to connect this result with many other branches of science that you already know. And one thing is that if you want to describe the progress of these particles inside this square here, but if you try to get beyond the horizon, then a very important concept is it's a so-called Cauchy surface. We have a time parameter, and as time goes on, here you are moving upwards from the far past, which is below in this picture, to the fast future, which is way up, where it says infinity with subscript t. That's the infinite future. By the way, this description of the Schwarzschild metric has been distorted a little bit in a conformal direction, so that in principle the angles in which particles move remain much the same, but infinity has been moved to finite points. You get a conformally contracted picture which shows in a more deep way the connections that you still get. But this Cauchy surface goes from the past to the future, and here and in the region at the right, which was valid for the Schwarzschild metric, the past is down and the future is up. But in the region opposite to that, region 2, the same time now runs in the opposite direction, and these two squares are then connected geometrically at the center point here, where one time goes up, the other time goes down. This is very strange and for some people very difficult to grasp and to understand. But this is essential for what I have to say next, because once you realize thoroughly what this means when you study these collections, you find that very interesting things happen. Please go to the next slide, slide 7. The coordinates which are most convenient to use are not the Schwarzschild coordinates which we had in the beginning. The Schwarzschild coordinate had a distance from the origin called r, then a time called t, and then the two angles theta and phi. Very natural to try these, and that was what Schwarzschild first did. But to get these two triangles, these two squares, you have to use different coordinates to see more clearly what happens. The coordinate x and y, whose product is a function of r only, and the ratio of x and y, whose ratio is the exponential of the original time parameter. So, so this is how the Schwarzschild solution behaves when you add these squares. But there's something very crazy going on in these equations. If you haven't seen them before, you won't immediately notice. The product of x and y is this, the ratio of x and y is that. But this is very bizarre, because if you take two variables and you fix their product and you fix their ratio, the two parameters themselves are not completely fixed. They're only completely fixed if you assume they are real, by the way. They're only completely fixed if you realize that at every x and y, there is another x and y, which is minus x and minus y. And when you replace x by minus x and y by minus y, then the top equation in this slide remains the same. But also the second equation remains the same. The ratio of x and y also doesn't change if both x and y change sign. What does it mean in practice? It means that if you change sign of both x and y, you're not moving at all. You stay at the same spot. But they do represent two different points. If you go back to the previous slides for a moment, the previous slide has a theta and a phi. But if you take an x and a y in this slide, x goes in the diagonal direction above. The y coordinate goes in diagonal connection in the other direction. These form the horizons. But if you replace x and y by minus x and minus y, you go to a completely different spot. In fact, you do that if you move from region 1 to the same analogous spot in region 2. So take region 1, take region 2, and then, if you go a slide back for one moment. Well, never mind. Oh yes, here it is. Here you see that what I said is that the grayish particles cross a line here. This is the line where x, where one of these coordinates changes sign. Here's the other line, the other coordinate changes sign. But every point in this diagram has one counterpoint going to the opposite direction. So in region 1, all those counterpoints are in region 2. Or if you're on this horizon, then all these gray arrows downstairs go to the gray arrows upstairs. So there's an ambiguity when you write down these coordinates. People realize this quite clearly. It is beautifully described by Hawking and Ellis in their book. And many people make use of this fact. But few people go as far as I now propose. I would say, yes, this happens when you make an analytic continuation. But no, this analytic continuation is not physical. What it is instead, I'll try to tell you. It's not easy to explain. It is very important, that much I say, but it's also true that there's no quadrangle 2 if you have a quadrangle 1. And one reason for that is that the only allowed shape that you can get with these two coordinates is a region 1 and a region 2, but they are identical. You can't choose region 1 bigger or smaller than region 2. You can't use it to go in a different direction. No, there's only one region 2 that is clearly the counterpart of region 1 and vice versa. And that's because at every x and y there's exactly one other counterpoint, x prime, y prime, and not 2 or 3 or more. And this makes that there's something much more special going on. There's something, let me betray right away what that something special is. My belief is that region 1 describes not all the Dirac cats of the theory, but only the Dirac cats, but not the Dirac bras. So you have the Dirac bra cat, which form in the formulas they form such a shape. Now one of these sits in one triangle, one quadrangle, the other sits in the other quadrangle, and so that's a much more special role that they will play in my quantum theories. Unfortunately, my quantum theory is far from finished, and there are many things I hoped to do a calculation before I started this lecture, but that was impossible. These calculations are quite hard, so I haven't done everything. I haven't controlled everything yet. But now let's go to slide number 8. And slide number 8 tells you that there's a big advantage to this new coordinate frame. By the way, it's called after Kruskal and Sekeres. The Kruskal, Sekeres, or Kruskal coordinates are like that. But the remarkable thing is that it's even less singular than the Schwarzschild method. The Schwarzschild method, you have to continue beyond the horizon, and then you get this divergence on the horizon and divergence at infinity. But in these Kruskal-Szekeres coordinates, there seems to be no horizon. Well, there is no horizon, turns out, but there's no singularity associated to it. So it looks like that these Kruskal-Szekeres coordinates are more fundamental than the Schwarzschild arrangements of the points that are essential to describe what's going on. Now, I don't know how many of you will know the notion of a Rindler spacetime. Rindler spacetime is what you get if you do the same thing, not starting with Schwarzschild, but starting with the vacuum itself, just flat space. In flat space, you can also make transformations. Turns out quite recently that there are much more transformations you can carry out in flat space that are equally interesting for gravity theory. But I won't touch upon those. Those are new developments. But there's a very important difference between Rindler space on one hand and the Kruskal-Szekeres situation, KS, on the other. So there's something going on that needs to be considered very clearly, and that is that there's a fundamental difference between those two. And this difference was not noticed or appreciated very much by many other people, in particular not by Hawking, to my surprise. Stephen Hawking has concluded that you can use Rindler space as a model for black holes. As a model for black holes that are not formed by an implosion or something and also won't decay at all at infinity. So in that sense, the Rindler space is a bit different from Hawking's description of a black hole. And Hawking did not, to my mind, did not sufficiently appreciate that you have to take this difference into account and discover that one is not easy to displace by another. But I'll come back to that when I have time for this. What happens instead, and I'll go to slide number 9. What happens instead is something that is beautiful in physics, very important and very mysterious at the same time. You may have thought that quantum mechanics is mysterious. No, general relativity is even much more mysterious. Because I can take the original Schwarzschild solution on this slide, which is the brownish square where the coordinates are called r and t. There's only one such coordinate frame to describe a black hole. But if you use the x and the y for the Kruskal space, you get two frames. You get the left quadrangle and you get the right quadrangle, and they both overlap in a way so that every point on the left quadrangle has its counterpart on the right one. What I did here in this picture is I drew both these squares in one picture, showing them as if they are transparent. That is just to indicate that every point on the blue square also has a point in the xy square. But of course it also carries on a point at the Schwarzschild solution. So the Schwarzschild solution didn't disappear with the advent of these two new descriptions. It is just a different way of arranging the coordinates. You can arrange the coordinates in 3 different ways, as displayed here. The blue, the red, and the brown surface are basically the same surface repeated 3 times, or repeated twice, of course. And those repetitions suggest that there's much more physics going on. Quite to the contrary. If you describe a black hole correctly, you only need one of these 3. It doesn't matter which. You can take the blue one, you can take the red one, but you can also take the original brown one. But every single point on the brown surface is a single point on the pink surface and a single point on the blue surface. And now comes the most miraculous statement. Not only does it hold for the phenomena that we are seeing when we look at the black hole, it also holds for the observer himself. I drew here a little man. This is the observer. There are 3 observers, each sitting in a different place, so to see. The observer will disagree. The observer will say, no. There's only one place where I'm sitting. That's here where I am, where you see me. Yeah, but we see you in 3 different places. So, and the important observation is that you can do physics with that. It is very hard, and it is different from quantum mechanics. In quantum mechanics, it looks like this is fundamentally impossible. You can never make a clone of a given configuration somewhere else. The different configurations will evolve differently, even if you start out with them having totally identical. Well, here I say goodbye to quantum mechanics, because for black holes, these 3 things are 3 copies of the same situation, which are just 3 copies of the same truth that we are describing. So now my question will be, so where does it occur in quantum mechanics as well? And of course it does occur, and it could occur in the Rintler space. It doesn't in ordinary Rintler spaces, but if in a Rintler space I can make the same change. I can say that the Rintler space consists of 2 halves of our universe. What happens in these 2 halves is totally different in one than it is in the other, but we can take them together, and then we can now postulate that also the quantum mechanics is the same. For instance, there could be the universe could be folded up such a way that it forms a donut, and then in the donut, if you go around, you enter into the same spot where you were before. This happens for donuts. It happens for the Kruskal space, but it happens also for black holes themselves. But this is a very important feature of the geometry that you have to learn to appreciate and use quantum mechanically. What does it bring us in quantum mechanics? Well, I have a theory about that, which unfortunately I was unable to prove. I tried with many people, they didn't believe me. My theory is that this is more fundamental, this picture here, and if you do this, you also still calculated that black holes emit radiation. But they only emit radiation in these 3 angles the same way. So if it emits a very exceptional particle, a particle that is exceptional because it is too big to be allowed thermodynamically, but it can still happen every now and then, the same particle will also emerge in the red region, and the same particle will also emerge in the blue region. In that way, working with probabilities will be unfamiliar, and therefore gives results that you might not believe. The theory I have now, which I couldn't prove as yet, but I'll still try after this lecture is over, that the repetitions here are true zombies. They are clones. They are not real. They're not physical, but they are connected together, just like space and time in a torus can connect together if you go full circle in a torus. In that way, it is connected. And but the Hawking temperature that you compute this way comes out different from what Hawking thought. Hawking was so proud of his temperature, he wants to have it on his grave, but I'm not sure whether he has the right temperature on his grave. My first impression was that the temperature will be twice as big if you do this, but people deny that. I'm sure that Hawking was correct in his calculation of temperature. It could be. I'm not saying he was wrong, but there was something very strange going on. If you look at the different domains of the same metric from different angles, and you see these clones have to be handled especially if you apply quantum mechanics. In fact, they have to be applied just like you do it when you are looking at space and time on a torus. So let me now go to the next slide. Yeah, let me see here. Yeah, it's better. So this is what I said there, and now the thing which I haven't yet mentioned, I mentioned that on this slide, is that I mentioned in this slide the conical singularity. There's something that happens, and that's unavoidable, and that is at the central part of this Kruskal-Szekeres coordinate frame, where all these things come together. That point is not an ordinary point in space-time. It is a singularity. It is not only, well, we have learned to believe that all singularities in physics are just consequences of doing the wrong physics. And if you do it correctly, you can unfold these spaces and singularity disappears. What you can do, like in Schwarzschild and to some sense also in Kruskal-Szekeres. At that central point, you cannot do this. at the central point only works properly if it is a singularity by itself. Not so much kind of singularities that most of you are used to, but it's a conical singularity. Well, conical singularities differ from other singularities in mathematics, in science in general, in the sense that although it is a singularity, the space-time equations can take a new form on that point, only on that point, not the surrounding points. But the conical singularity, you can do something about them which you cannot do in other singularities, for instance, not on horizon singularities. But on the cone, what you can do there is you can soften the singularity a little bit. You can say, well, it's an infinitely sharp point. Yes, but infinite doesn't belong in physics. Finite, but very sharp points, yes. So my claim is the conical singularity in the Kruskal-Szekeres coordinates is a very singular point, not infinitely singular. Why is that? Well, you know in general relativity that the curvature of space and time is caused by matter. So if you have no curvature at all, you have an infinite singularity, then you don't see anything out of the ordinary, you don't see any matter. But the real black hole has matter in it all the time, and that is those imploding particles which made a black hole. You have the particles come together to make a black hole, and those particles will not go away, but they do come very, very close to each other. And the singularity in space and time that they do generate is, according to my theory now, that conical singularity. The same thing happens when a black hole evaporates. The black hole emits radiation. Radiation goes far away into the rest of the universe, never to come back. So the black hole then says, well, then I lose weight. Eventually the black holes lose so much weight that they disappear altogether. That also is a singularity. And that singularity is also a conical singularity. In fact, it's the same. So the same singularity that you see by matter condensing to a point, making a black hole, that same singularity causes very dense matter to get out of the black hole. By the time it gets out, it's very smooth and very thermal. Yeah, thermodynamics comes in the story. And this here altogether, you get a new way of describing black holes. It works better than the description that Stephen Hawking gave. Because you can ask me now, why did I put this conical singularity on the horizon? Well, not for nothing. There's a problem. The problem which took much of Steve Hawking's attention that should be dealt with some way or other. And the problem is that if you throw matter into a black hole, it doesn't come out, so to say. You can't see it coming out ever, so that matter just disappears. Not only does the matter disappear, but also any vague remembrance of those particles disappears. And that means that the black hole violates a principle of nature. The principle of nature is that however singular you try to make things, if it's not infinitely singular, then you cannot lose information. The information will somehow come back to you, not in a recognizable way. Think of stirring the milk in your coffee. If you stir a few times, the milk has been equally spread all over the coffee and you don't see any structure anymore. That does not mean that there is no structure. No, the coffee consists of a finite number of atoms. A very large number, yes, but finite. Because that number is finite, also the amount of time that you need to unstir your coffee will be a very large number. So that means that quantum mechanics here also is going to play a role. Finiteness is not what it seems. Thermodynamics is not what it seems. And the one-way direction of time is not what it seems. Time can go back as easy as it go up, as it go forwards. And that you can see by looking at the Schrödinger equation, for instance. The Schrödinger equation can be solved forwards in time, but exactly as easily backwards in time. So the Schrödinger equation is completely time reversal invariant. That is also true for the information on a black hole. It behaves just like the coffee being stirred. So the black hole is large but not infinitely large. If it is infinitely large, it doesn't evaporate. But if it's just very large, it consists of a very large number of elements, and they together play this game of information in a way like a soccer match, but not with 11 players, but with billions and billions and billions of players. Where is this ball? Well, it's very hard to follow it at all. People call that quantum mechanics. I call it just exceptical forms, equations of matter, and not at all singular, not at all doing any harm to information. I think information comes back. I'll explain more why I do that. Next slide, please. Oh no, I don't see the slide, next slide anymore. Yes, what you see in the next slide is how, if you see slide number 12, do you see slide number 12? In slide number 12, I draw again one square, believing, as I said, that the two squares, the second square of that is not physical. It's mathematical, mathematically very important. What happens instead is that if this second square region wasn't there, then the information that goes into a black hole can go out, but then it can never go back anymore. The only place where that information thrown into a black hole can come back to region 1 is by entering this space from the past. So here you see something miraculous happening. A particle disappears in the future, does something unknown, and then reoccurs at the past. This is the only way to avoid the problem that haunted Stephen Hawking so much, that you can say, well, in this way, the information can stay preserved. All these particles can carry with them, no matter what kind of information, all that information will be found back in the particles that emerge from the black hole in the far past, as if they went full circle around. Going full circle around is asking for difficulties, because now you see that the equations of motion become periodic. A particle can go around many times. Periodic motion sometimes occurs, but generates finite periodicities. And certainly if you use a finite number of numbers, finite numbers in general, then the same particle will come again and again and again going around in circles. This can happen in physics also, and the clock, which I don't have here in my room, but I have a clock which has a wooden pendulum, and that clock has certainly a periodic motion in its pendulum. And that's a marvelous example of periodicity in science. So this generates periodicity, but of the kind actually that we need, because quantum mechanics, its equal energy solutions always carry fluctuating, oscillating degrees of freedom. So this generates oscillating degrees of freedom, and that which is not something to be concerned about, but something to be interested about. How can we understand what is conical, what is this divergent behavior, what it means? Can you show the next slide, please? In the next slide, I show you what happens. This grayish region that you see here, I don't see my next slide in my examples here. But can you see a slide with a grayish region here? Slide number 13. Can you nod or not? Well, anyway, what you have to do is introduce the conical singularity at the central region of the original Kruskal-Szekeres coordinates, but cut off half of all you see there. So that is not only a conical singularity, it is a very conical singularity. It hides away 180 degrees from space-time. That's exactly what you need if you want this, whatever matter that comes out here, if you want to have that return back here. And this scheme works amazingly well if you take into account some other things in science. Let me, now I don't see. Wait a minute. Yeah, I have it now also. So in this slide, yes, I explained to you, this angle was not drawn exactly 180 degrees, just to see my point. My point is that this will just be a straight line, and the particle cutting out here will directly come out here. And the reason why they do that and why this works is a beautiful scheme that has to do with quantum mechanics. I'll try to explain that. And that is the so-called Shapiro shift. I'm now at slide number 15. And slide number 15, you see the Shapiro effect. The Shapiro effect was that, and when you have, this is the sun, obscure so that you see that it's a sphere. The sun, this is a light ray of a distant star passing the sun from close. That light ray is being bent. This is the so-called Shapiro effect. And this bending in light can be calculated, and the equations are rather simple. That is that in general relativity, the effect is twice as big as it would be in classical relativity. But apart from that, it's a very important effect. It plays again a role in black holes. In black holes, we replace the sun by a heavy particle, and this light ray passing the sun we will replace by a very light particle. The heavy particle will pull the light particle in a different direction. The picture next to here, you see the heavy particle is brown, the light particle is green, and the light particle is now being dragged along by the heavy particle. It's a slightly different effect because the velocities are different. The sun here stands still, here it moves very fast. The green particle moves also very fast here, and it's like a light ray. That's the light ray here. So this is the effect that particles have on each other. Well, the black hole particles falling into a black hole, they pass the other particles that were far away from the black hole. And you can see that if you go 2 slides back, slide number 13 for a moment. 2 slides back, can you do that? One more. Yes, here. No, yes, here. You see that the particles that are getting out and pass sooner or later will cross the particles that are getting in. The crossing will be very mild as is drawn here. The velocities won't be very big anymore when they are here. But the velocities become very close to light when you wait a little bit. When you wait a little bit, these particles are not seen to come out here, but they're seen to come out here. And the particles that are getting out are not seen to be getting out here, but they are seen to be getting out here. At this point, these particles have very strong relativistic velocities. And now the Shapiro effect becomes significant. The Shapiro effect tells you that the displacement caused to the outgoing particles by the ingoing particles grows exponentially if you get very close to this point. So very soon, the ingoing particles will simply put the outgoing particles somewhere else than where they were supposed to be going. And this effect becomes big, therefore it becomes an essential effect, and it changes all the physics that we thought we understood about black holes. Many people throw this away. They say, well, that's a thing to be concerned about later. No, it's to be concerned about right now when we try to understand where all this information goes. Because if you just wait long enough, then the outgoing particles go out very far away from the center. You still see some relics of outgoing particles going further and further out. But at some point, the outgoing particles were very close to the ingoing particles, and therefore, their separation was very small. You can say, hey, wait a minute. We thought that fast-moving particles give bigger displacement than slow-moving particles. Yes, but here they are going in the other direction. So what is slow-moving here is fast-moving there. So this fast-moving particle gives a slow-moving particle getting out. The longer ago it gets out, the further away it is from this horizon, and the slower it goes. But the nice thing about this effect is you can compute it. It's very basic. We understand the Shapiro effect, so we can compute this effect. But it's true that momentum here is affecting position here. And now I say, hey, here comes quantum mechanics. Momentum and positions are each other's counter effect. And yes, that's what happens here too. That the momentum of this particle affects position here. In quantum mechanics, the opposite is also true. The momentum of these particles affect the position there. Yes, if you rearrange these things a little bit, you find that what I called momentum here now looks more like position, and what I call position here looks more like momentum. It goes both ways. But it is an effect which is so important that it can return the information that went away. This particle may have gotten out very close to the horizon, but this effect will bring the particle away from the horizon to see us. But you only get that if you have particles here. So these particles which are getting out of the black hole, as you look carefully at the arrows, those particles have this very important effect that they carry away information, but the information is distorted because momentum was replaced by position. And but now you can see, if you do this sufficiently carefully, you can see that now information is conserved. Provided that this conical angle is exactly 180 degrees. It should not be less than 180 degrees, then it doesn't work anymore, geometrically. So now yes, this is the other thing I want to say about the Shapiro shift. It is symmetric. So if this is the fast particle, the green particle is now a fast particle. Oh, and slide number 17. Yes, now here the green particle is a heavy particle, so it drags along the red one, which in this frame that it shows here is a slow particle. So now that one is being dragged. So it works both ways. And of course, you know that's the way the Fourier transform works. If one field is a Fourier transform of another field, the other field is also a Fourier transform of the original field. Fourier transformations go both ways. If you go from momentum to position, of course you are performing a Fourier transformation. So this now is a first indication as to how the ingoing particle affects the outgoing particle. And when you do that, you find that there's indeed very interesting new physics. I still have a couple of minutes left for my talk. And what I want to say is that this is only the beginning of theory. We should understand how this effect can also affect the temperature of a black hole. This is much harder than in the original Hawking calculation. So I wanted very hard to have this problem out of the way before I gave this lecture, but no such luck. It's still there, how to do this calculation correct. But my belief is it will double the Hawking temperature. So this conical singularity, which removed half of the Kruskal-Szekeres coordinates frame, now doubles the temperature. And the reason why I say that is that if it removes half the space, then you've removed half of the entropy that you get in this world. If you divide the entropy by 2 and you do thermodynamics, you have to raise the temperature by a factor 2 in order to get the equations to fit together again. So my belief is that the black hole radiation will actually be twice what Hawking calculated if you follow this particular prescription. But in practice, it's still a very hard calculation, and we have to understand very well what we are doing. And that is, again, the difficulty here. You need to, you can come with many good ideas, but you often need to be an Einstein to solve the equations. And I'm not an Einstein, quite to the contrary. My mental health is slowly going back to where it was when I was born. So that is a problem, and I don't know who's going to solve this problem. I think I know how to do it, but it's still hard to get it done and be sure that it's correct. So now I wanted to spend a few more minutes on the same kind of observations one can make in quantum mechanics. In quantum mechanics, there are whole hordes of people who follow each other's ideas and try to make it look better, and who try to emphasize the mystery in quantum mechanics. Quantum mechanics, they say, is a theory full of mystery. Not so. If you do it right, and if you realize that large numbers are very difficult to understand, even in classical mechanics, in quantum mechanics, the numbers generated by the equations are often exponentially much larger than the large numbers in statistical physics. So those numbers are so ridiculous that things happen that you often don't quite understand. And one thing that happens that I am convinced of, now I have more equations to use to see why I believe this is correct. And that is about the ontology in quantum mechanics. Can you go to slide 18, please? Oh, yeah. Ontology in quantum mechanics. Many people believe that when you do a Bell-like experiment, that these two spin 1/2 particles that you're looking at cannot be real. They are doing something, we don't know what they're doing, but they cannot be described by reality. And this was being proven by Bell. When someone proves something, you have to realize that you're proving something about a theory which hasn't been formulated too well yet. It holds for gravity, it also holds for quantum mechanics, even sometimes holds for thermodynamics, because even there are paradoxes, as you may know. So you have to watch very carefully what you're saying. When you believe that quantum mechanics will kill ontology, I believe it won't, and actually to some extent this time I can prove it. And I'll try to use the arguments. Please go to number 19. This is already what I've said, that they claim that John Bell has made a thought experiment, and that with his thought experiment they can prove that whatever made these two spin 1/2 particles cannot be real. And that's because you can send informers there, but as soon as you're looking at the status of these particles, these objects that produce these two spin 1/2 particles, you find that one observation spoiled the other. John, of course, realized this, so he said, yes, so all I have to believe is that the sources of these spin 1/2 particles obey certain laws of statistics. And the laws of statistics that I'm going to demand is that these two sources that created two objects which are moving in Bell's experiment, that this object which made these two particles are statistically independent. He doesn't describe what statistically independent means, and that's the weak point in Bell's argument. He assumes that a thing came from here. It could be a photon, could be a spin 1/2 electron, could be anything. The thing that was produced here and the thing that was produced here, they have been formed, must have been formed by different objects, different structures, which are ontologically speaking independent of each other. If you open an insurance company, you open insurance for the particle here, but not the same insurance for the particle there, then you find that you can't prove what Bell wanted to prove. So there's something hidden there that is simply pulling quantum mechanics where it shouldn't be done. And this time I can prove it. I'll try to use the last few minutes for that. This slide number 20 is slide number 20 is showing what I already said, that the data produced by John Bell are statistically independent. But unfortunately, he doesn't know what statistical independence means, because insurance companies do know that if an accident happens with more probability here, it will happen with less probability there, and they can compute how probable an accident will be that you want to insure, or whatever you want to make your insurance about. And there's no mystery in the way insurance companies act. Everything is quite clear and in the open. But one can construct models where you can see where it goes. And one way to ask a question to Bell, to which I think he wouldn't have an answer, is all laws of physics that we know of are invariant under time reversal. So if I replace future by past, well, you saw it in the Kruskal chaos diagrams, that if you replace future by past, it looks identical. And in many physics experiments, when you look at the collision of particles remains the same general structure when you turn it backwards in time. So many things are even under time reversal. And now take Bell's experiment and take these statistically independent sources of these particles that he wants to study. They now lie in the past and not in the future. In the future, but not in the past. In the experiment, these statistically independent particles were there in the past. In the past, you can say, I know nothing about the past, so they must be all statistically independent, and that's where my theorem holds. But if you switch future with past, you say, well, now let's look at the experiments. You see these two spin-on-half particles coming, you see them collide or not collide or do something else. But now you suddenly generate a perfect statistical independence of wherever they are going to, quite to the contrary. They generate chaos and they make things more complicated, certainly not perfectly statistical. So perfect statistical physics is more complex, more difficult to understand in quantum mechanics than people often believe. And given now your favorite paradoxical quantum model, everyone here has his favorite, then I can show that I can write down all hidden statistical correlations among the variables of this theory such that the paradox goes away. It is still a beautiful experiment, interesting to be done, but you can say something goes wrong with the paradox, and the reason being that the sources which makes these particles do that trick, these sources are not as statistically independent as you thought. Even if those two sources were at different points in the universe, different points in the universe are not statistically independent. It's going to be hard to do that experiment, but that shows that maybe not everything is lost in quantum mechanics. Easy things can be done easily, hard things can be done hard, but impossible things can be done impossibly. That's when you do the Bell experiment with the size of the universe. So I'm not worried about that at all. There's a very nice example of a paradox, which is the Greenberger-Horn-Zeilinger paradox, that there are three particles, and there people were even more convinced that this is easy to do experimentally, and yes, you'll find that the equations that people thought they could write down don't hold. But the equations require a kind of independence that's impossible to reach in practice. That's my bottom line. So, and here comes, yes, I'll go on for a few minutes. Here comes a little theorem that is, I consider two models, model A and model B. And suppose that these two models, they're now a model of experiment, but the experiment including the statistically independent or dependent sources that you have in the past. I put them all in a model. And the models are called A and B. And now let's assume that both models have one peculiar property, which is that if you look at the solution in momentum, in energy space, if you look at the energy spectrum of the quantum states of the model, you find that the two models A and B have the same spectrum. That is an interesting thing to exercise to do. I can recommend it to anybody. Take two things, give them an energy spectrum. Now compare the energy spectrum of one model with the energy spectrum of the other. Claim these two models are physically the same. You can't ever find any difference in the two models. So you can do any experiment with one model and do the same experiment with the other model, they'll give the same answers. So that's a consequence of their energy spectra to coincide. And an amusing exercise is to apply this theorem for a model where this fact can be proven to be right. And that is a harmonic oscillator. The harmonic oscillator is an object that has an energy spectrum starting with 0 excitations, 1, 2, and so on, all the integers, all the way to infinity. There is another model which has the same property, and that other model is the classical particle running over a fixed circle. So compare the oscillator's position in the periodic space, compare that with the position of a particle in a circle, these models are completely identical. So you can never see in which of the two models you work. You work in both models simultaneously. All observables that exist in this one model can also be reproduced in this other model. It's very easy to see why the quantum mechanical harmonic oscillator has dynamical equations like quadratic force depending quadratic on distance and so on. But the other particle running over a circle just runs with a constant fixed velocity around that circle. And now you can see that these two models have the same energy spectrum, because this model is also easy to compute the energy spectrum of. There's also a sequence of infinite numbers. And if you take this particle to be continuous, you get a continuous spectrum going into a circle. But in the discrete case, then the circle has only a finite number of spots for a thing to sit. And oh, sorry. So so you can see that these two apparently totally different systems can be compared, and all the observables are the same. Now, one of these models is classical. It's the particle running over a circle, has nothing quantum mechanics in it. Yet, when you treat it with quantum mechanics, you can always do that, you find the same energy spectrum. But that means that all these states corresponding to those energies in the case of the periodic curve, all these states are real physical states that you can have in this model. You can put this necessity where the particle sits in one spot on the circle and then moves around. So you can choose that spot. I can choose that same spot for the harmonic oscillator. It's a bit more difficult because I have to take the solution of the harmonic oscillator in energy space. Yeah, it's the same solution. So I then identify those spots with the same elements in the circle for the particle moving on the circle, and identify these two spots for both models, find that they are identical. They also evolve into each other in an identical way. And that's guaranteed by the fact that they are energies, and the way the problem evolves if you let the energies go along circles, that is exactly infinitely precisely defined. There's no mystery whatsoever in that. I call this model the quantum grandfather clock, because of course the pendulum is like the pendulum in the grandfather clock, but there's hands going around, it's linearly in time, and okay, my quantum grandfather clock has only one hand, but leave that detail aside for a moment. Then you find that it also has this property. So I say you can quantize the grandfather's clock, and for both you can solve the Schrödinger equation. So the Schrödinger equation for the harmonic oscillator is something like this, and for the particle moving in a circle is like this. Now I can say I can identify the degrees of freedom here to degrees of freedom here. Since I can identify them, I cannot distinguish them anymore because they're identical. So it's not possible to distinguish the pendulum of the clock with the hand as it goes around the circle. And now this is my last slide. Last slide says 26. So can we introduce interactions in this model? Because I imagine some of you saying, well, this is too fantastical. I don't believe it's true. Let's ask him about interactions. Well, ask and I'll give you an answer. And a more complicated configuration is that you take not one circle, but you take very, very many circles with different radii. So the particles go with different speeds in these very many circles, and then put many switches in there as well. So when a particle hits a point, it touches a switch. Now you have interactions, because this can become about as complicated as any other model in physics. So there's an open end on how many complications you can bring about. So sooner or later you'll hit any model you like by making this transition. And that shows that how you can probably avoid quantum mystery out of the theory of science. If I were younger and more juvenile, then I would be carrying a banner now. Get the mystery away from quantum mechanics, gave the way to ontology in quantum mechanics, and I would wave it very hard. But now I just wave to say goodbye, and I would like, if possible, to have a discussion if people found out a way to get sound back in this transmission. Thank you.
Thanks, Professor Toft. I don't know if you can hear me at all.
I don't hear you, so how do I get these messages? Here I see one question. May I read it for a moment? Yes, that is fine, of course. It is fine to put everything on an email, and then perhaps I get similar or the same question several times. That's also fine, and I can try to answer all these questions that you may have.
Thank you. Thank you. Thank you. I'm just so all I can do is an applause. I don't know, since you're not able to hear me, I don't know what to.
No sound.
Thank you. So for the rest of us, this has been put up on the chat. You're also seeing this on the screen. Professor Toft has also confirmed any questions that you may have, you can put on the chat, and just make sure that you write your email and name, and I'll make sure that I email the queries to Professor Toft and also the replies to you. I don't know what to say. Anyway, so this is 6:15 here, around 6.
It was my pleasure to give this lecture.
Thank you. Thank you. Yeah, so we have the next talk is in 15 minutes from now. And so it is on the same link, this particular Zoom link. Yeah, so you had to say something, Didi?
Professor Rao has just posted a question.
Right, so it's going to be emailed to him. So because he cannot hear it. Maybe I can make you the co-host so that you don't. Yeah, go ahead.
Can you put it on the, slide just the way you have? Because it seems, just read the question.
Well,
You
reading.
can put it on a slide and put it if you have time.
Let's see. Rupa, can you do this? Yeah, I just have to copy paste. And this is Professor Rao. A caution regarding slide 23. Just copy this to a PPT and just share it on the screen. Okay. All right. So I don't know how to convey this to him.
And Professor Patrick Dasgupta has also written a question.
Well, I mean, we cannot do this. This is because I don't know whether this question is being will be.
All right. There is already there's another one from Anna.
So I would, as I said, I would be emailing all the questions and then therefore emailing back the replies. So that's how it's going to be. I really, I don't know, it's unfortunate, but at least we had the talk uninterrupted once it started. So I'm really sorry. But I think Professor Hooft is not really, I mean, he is in a place which doesn't have good connectivity. He had sort of forewarned me earlier. There are some issues that are there. So yeah, that's the best we can do at this point. Sorry again. So we are waiting for Professor Robert Wald to join. It should be, yeah, soon. And as I said, it is on the same link. Yes, Professor Panchpagation, please. Maybe I can make him the co-host.
Yeah. Wondering, do we have to switch off and then join in again?
No,
Or-
not at all. No, no, please continue. Please.
So it will come here continuous.
Yeah,
Thank you.
yeah, absolutely. Yeah.
Mhm.
Hi, Professor Wald, can you hear and see me? This is Alok.
Yes, I can hear you and see you.
All right, great. So it's after let's see, more than 18 years that we are meeting again.
Yeah. Yeah.
Okay. So, all right. Would you like to share your screen and your presentation
Yeah.
so that we can just have a look?
So is the other talk going on now, or is that?
Yeah, Professor Toft just finished his talk, and you're up next.
Okay. So does that work?
It does. Can we go full screen by any chance?
I can try. How does that? I mean, you're only seeing the PDF, I assume. I can do that, but that usually doesn't work for some reason, and then I can't see the Zoom stuff. But let me. I'll. If I go full screen mode.
Okay.
I'm only okay.
That worsened these. Yeah, I think we're good the way it was earlier.
Yeah. Okay. What do you see when I go? I mean, I'm seeing the full screen, but
now we've seen just a vertical strip of like the options that you get on a PDF. You know, the arrow, the what you can draw the wiggle and the text box.
really, okay.
So everything
Is, that's ridiculous because I'm seeing the proper thing. Yeah. I mean, is the yeah. What is the deficiency with what it is right now? I mean, is it too small or is it?
Yeah, actually, we don't see anything except that vertical strip. So perhaps you can.
No. I mean, I've gone back to the non-full screen. Is that all you?
No, but we're still seeing the old single strip. So maybe you could unshare and share again, please. Yeah.
Yeah.
Let's go back to the original format, if we may.
Is that working?
It is working. It is certainly better than getting just a vertical strip. We don't see the full page. Okay, that's my problem.
Well, okay. That first page. Okay, what do you see? Like on this slide, do you?
This is good. This is good.
I mean, I can. You're only, yeah, or this slide.
Yeah, it's all good. It's all good.
Okay, and this first slide, is it being cut off at the bottom or?
No, I think we're good. We're good. Yeah. It's fine. It's fine.
Okay.
Great. So I think we have about 4.5 minutes to go.
Yeah.
Maybe we can give folks some chance to join. They are trickling in. And yeah, so we have the chair of the session, Professor Patrick Dasgupta. So he is on board, and he's going to be chairing your talk. And so we start at 6:30 our time, and the time I forgot what it is in Chicago.
8 a.m.
8 a.m. 8 a.m.
Yeah.
And if I recall, you have a class right after the talk.
No, I'm teaching Tuesdays and Thursdays, but I actually have a flight to catch long after the talk. I mean,
Okay.
Would need to leave here in about 2.5 hours, but there's no problem with an hour and a half of the talk.
Excellent. Yeah, we promise we're not going to keep you any longer than that. So that we get. Okay, so right. So Professor Patrick Dasgupta, it's you're the boss of the session. Please.
Shall I start the introduction?
Perhaps, if you wish, we could wait for a few minutes.
All right.
Yeah, we might as well wait until 8 o'clock.
Yeah, exactly.
Or...
Yeah.
All right.
So this is the talk is entirely online. I mean, everyone who's joining is joining separately online as opposed to this being displayed in an auditorium or something like that.
No, it's the first what you said, that it's everybody joining online individually on the devices.
Yeah.
And this is being of course this is on Zoom and is also being streamed live on YouTube. And the videos, and we'd also request you to send in your presentation file so that the file and the video of your talk is available online on the lecture series website.
Okay.
I'm just curious, Professor Wald, by any chance, do you have a green screen behind you? Because you've got a beautiful picture of the campus.
Yes, well, I don't have a green screen behind me, but I do have the Zoom background of University of Chicago campus.
Oh, okay.
Yeah, that's not the view out my window.
Okay. Maybe just we have about a couple of minutes to kill. So maybe I can just give you a little background of the series. So this is something which was started a few years back, and Professor Panchbakeshan, who's online, was the first lecturer of the series. And that was when it was we were just coming out of COVID, and then we sort of went to an online mode. And so that was last year. We had Ed Witten giving the lecture last year, and there was also a meeting of online talks of other people. And so this year we've had so, like, for example, Professor Ashoknath Mitra, in whose memory we are having these lecture series. One of the things that he's globally known for is his work on few body physics. So we had a small few body physics session yesterday, followed by a lecture by Professor Pran Nath. Today morning, we had Andre Linde, our time morning, that is Pacific time night. Then we just had Professor Toft, and now it's you. So
Yeah.
With that said, we are at 6:30. So Professor Patrick Dasgupta, please.
Right.
Okay.
So it's a great privilege for me to introduce today's speaker. Professor Robert Wald is one of the most outstanding theoretical physicists. Right now, he is the Charles Swift Distinguished Professor at the Enrico Fermi Institute at the University of Chicago. Among many honors and awards, last year, he won the Dirac Medal as well as the Albert Einstein Medal. And his work spans a diverse arena of physics, classical general relativity, quantum gravity, foundational aspects of time and gravity, gravitational collapse and cosmic censorship hypothesis, black hole entropy as a Noether charge, the role or rather status of various conserved quantities in general relativity. Similarly, if you have an embedded rotating black hole in magnetic field, how preferential one kind of charged particles would trickle in and make the rotating black hole charge. So these are many of the exciting predictions that Professor Wald has made. I would not like to hold you between Professor Wald's lecture. So I would request Professor Wald to begin his lecture on black holes decohering quantum entanglement. Professor Wald.
Hey, thank you very much. Right. So, in fact, an alternative good title for this talk is Black Holes Are Watching You, but I don't like to give that as the title because I don't know what kind of audience that might draw. So what I'm going to be telling you about, well, is related to work that I've listed 5 references here. There was some work with a group in Vienna that really got me started thinking about these issues. And the other work has all been done with my now former students, Dane Danielson and Gautam Sadaschandran. Dane is now a postdoc at MIT, and Sadaschandran is now a postdoc at Princeton, but about to move to MIT. So he'll be back together with Dane. The work is mainly based on the 2 papers that I've highlighted in blue, in case people want to dig a little further into the details, a little further than I'd be able to go in this talk. Okay, so what is the talk about? Let's see, my forwarding is not working, so I'll have to do it by mouse. So the talk is going to be about decoherence, and this is very common and in quantum physics, and certainly for people thinking about trying to make quantum computers or things like that, or doing delicate atomic physics or condensed matter experiments that are looking at quantum phenomena. This decoherence is something that has to be dealt with. So if you have a quantum system that is in a pure state, you can't normally completely avoid its interactions with other things that are around, which I'll just refer to as here as an environment. But the environment will respond differently depending on what state the system is in. So if your system that you're interested in is in some superposition state, and the different components of the superposition interact differently with the environment, that will entangle the system with the environment. And of course, the whole system, including the environment, will remain a pure state, at least if the environment was also in a pure state. But the system that you're studying will now be in a mixed state. So that is the decoherence phenomena, and the interference kinds of effects that you would get in a superposition will no longer be present. The 2 components, if they interact significantly with the environment and the environment states then become orthogonal, then the 2 components will completely decohere. So what I'm going to talk about in this talk is not the usual environmental decoherence, but the fact that the presence of a black hole will, somewhere near your lab, if it's far away, then the effect will be very small, but provide a fundamental source of decoherence. And the way it works is that the black holes basically, absorb radiation, but this will be very low energy radiation from your system and effectively harvest information from it that way and result in decoherence. And as I'll explain, one can calculate this in a, very simple but still precise and quantitative way. So that's what I'll be telling you about. But to begin with, I want to get everyone thinking in the appropriate direction. I want to begin with a Gedanken experiment in flat space-time, so no black holes here. This is just some ordinary, situation, except that I am going to be concerned with causality and things taking place at space-like separations. So we're very much in the context of special relativity, though not general relativity. So let me take a few minutes to explain this and see if we can get the thinking about this correctly. So we have a skilled experimentalist, Alice, who has a particle. This could be a nanoparticle. It doesn't have to be an elementary particle or anything. But let's say this particle, well, there are two versions of this experiment, one an electromagnetic one a gravitational one. In the gravitational one, these things have to have mass, but they're going to have that anyway. Let me, though, talk about, since that's much more familiar and easy to talk about, I'm going to talk about the electromagnetic version, in which case this particle, these are two components of a superposition of the particle. This particle has charge, and let me assume it also has spin, so I can separate it into two components with something like a Stern-Gerlach apparatus. Now I'm drawing here a space-time diagram, so forward in time is going upward in the diagram. And I initially started with a particle that has spin in the x direction, but I put it through, so say into the board, into the screen, but I put it into a Z Stern-Gerlach apparatus, so it goes into a 50-50 coherent superposition here. That happened way in the past, so I didn't even depict that. But now, over a time scale TA, Alice brings the components of this superposition back together, with some sort of reversing Stern-Gerlach apparatus. She's very skilled and able to do that. And I'm, of course, assuming there are no environmental effects, so there's no ordinary environmental decoherence. So when she brings this back, one might expect that if she was careful and the superposition was maintained, then when the components get superposed, the spin will be back in the x direction as it was originally. Okay, but now the twist in this problem is we have some other experimentalist who happens to be named Bob, but is no relation to me, and you'll see why I'm glad about that in the next slide when we see what Bob does when a black hole is present, but no black hole now. And what Bob is going to do is try to figure out which path Alice's particle took. And he's going to do that by measuring the strength of the Coulomb field of Alice's particle. Because if, again, the particle was separated way back in the past, if it went to the right, it's closer to Bob and there'll be a stronger Coulomb field than if it went to the left. So if he releases a particle, it will, from some trap, let's say, at some initial time, it will start moving toward Alice a little bit more, and will move toward Alice by the end of this experiment a bit more than if Alice's particle had gone to the left. So, of course, Bob's particle is quantum. He's not going to be able to do a perfect measurement, but again, he'll get some which path information. But the way quantum mechanics works, if Bob has some which path information, well, that really is meaning that Bob's particle is entangled with Alice's superposition, and that means that there must have been at least some decoherence. So when Alice brings her particle back together, there's some chance that the spin will be in the minus x direction when she measures the x spin rather than in the plus x direction. Okay, but now the final twist to this is I'm going to have Alice bring her particle back together and Bob do his measurement of which path. I'm going to have this happen at space-like separations from each other. These are null planes here that I've drawn. And from that, you can see that what Bob does is space-like separated from what Alice does. But that means that, by relativistic causality, whatever Bob does can't influence Alice. So the question is, does Alice's particle maintain coherence or not? Why not? Because Bob can't influence Alice. That's one answer. So yes, that would be that answer. But the other answer is no, she certainly can't maintain perfect coherence because Bob does get some which path information and thereby must be entangled with Alice. So if I were giving this talk to a live audience, I would pause and ask people who haven't read our papers, to give the resolution of this. I should say this is a Gedanken experiment that was originally proposed by Mari, De Palma, and Giovanetti, and it was thinking about this that got us on this whole trail. Okay, so instead of, since I don't know that this would work anyway, instead of asking people to make suggestions, I will tell you the answer. And the answer is that the perfect decoherence cannot be maintained. There will have to be at least as much decoherence as one would expect from Bob's measurement. But Bob has nothing to do with this, as he can't, because he can't causally influence Alice. And in fact, the cause of the decoherence is actually radiation that is emitted by Alice. These paths and the accelerations and so on are different, and there will be different radiation emitted to infinity depending on which path Alice's particle takes. And that causes the decoherence. And indeed, although it may not look like it from what I've said, one can interpret what Bob is doing as simply measuring some of that radiation. So Bob has nothing to do with the decoherence, but he can be interpreted as measuring the radiation that Alice's particle is emitting, which is the cause of the decoherence. Okay, so now the new twist to this is, what if we have a black hole present? And, well, Alice is now shown here doing her superposition and recombination, but let's imagine Bob, again, not me, inside a black hole that's somewhere in the vicinity of Alice. I mean, it could be far away, but Bob won't get a lot of which path information then. So, of course, Bob, well, inside a black hole is not a good place to do an experiment, and Bob is going to, in fact, fall into the singularity eventually. But you could have a whole sequence of Bobs, and now the difference between this and the previous experiment is there's no time limitation on doing the measurements inside the black hole, because those are always, by definition, causally disconnected from Alice. That is, things inside the black hole can't, by definition of a black hole, influence Alice. And if you imagine Alice is keeping her superposition open for an arbitrarily long time, then even if there's not that much information to be gathered by a particular Bob doing an experiment before he falls into a black hole, if you have a whole sequence of Bobs, one ought to be able to do over a long enough time a perfect measurement of Alice's superposition. Let's say I should have explained that I've drawn here. I should have explained this diagram, so let me take a brief half minute to do so. I've drawn a conformal diagram here, so I've compressed the entire exterior of the black hole region into this diamond here with null infinity being represented here. So this is really going out to, going out in this direction in null, along a null geodesic is, going out infinitely far by the time you reach here. I've drawn a black hole that's formed by the gravitational collapse of matter, and I've put Bob and his experiment inside the black hole. Because this is a conformal diagram and I can show infinite amounts of time, I've actually shown Alice's creating the superposition here, holding it open for a very long time. And then this is the part I showed in the previous diagram where she brings the superposition back together. And well, she'll emit some radiation, but I can again have her do this slowly so there isn't a lot of radiation emitted to infinity. But we'll see that isn't true for the black hole. Okay, so this is just what I've really already said in words, that Bob, or a sequence of Bobs, if Alice holds her superposition open for an extremely long amount of time, can get arbitrarily good Witch path information, which means Alice's particle has to be decohered. But the punchline on this is that what Bob does, just as in the previous experiment, can't be relevant to Alice's experiment. So it must be the black hole itself that's effectively getting the witch path information, and the black hole itself, which is decohering Alice and Alice's particle. And that is kind of a little hard to picture how the black hole will do that, one might think, and that's what the remainder of the talk will be about. Okay, so let me go back to the original Gedanken experiment that I talked about in flat space-time and just write down a little bit more with a few relatively simple equations what's going on. So we had Alice bring her particle together and look at the state of the particle when it's brought together. So there's a real problem, a fundamental problem in accounting for degrees of freedom, well, really of the electromagnetic field, in that at finite times where things, well, the particles have not gone all the way out to time-like infinity, and the radiation has not all gone out to null infinity, there's not a clean separation between a Coulomb field, which would be viewed as not having any degrees of freedom of its own, a Coulomb field associated with a particle, and radiation. I mean, you can break up the electromagnetic field that way, but that depends on your choice of time slicing, and it really is not very well defined. I mean, when you go to the Coulomb gauge, you're effectively doing that, but the Coulomb gauge, if you boost your time slice, you get a completely different breakup of the field into radiation and Coulomb. But at asymptotically late times, there is a completely well-defined breakup. The Coulomb field of a particle travels with the particle asymptotically to time-like infinity, and the radiation all goes to null infinity. So if we look at asymptotically late times as to what the state of Alice's system and the radiation is, well, Alice's system will be described by some spin state and some spatial wave function. We've brought the components together so the spatial wave functions are now the same, and this is the spin up and the spin down components that I was showing before in the diagram. But this component is going to be entangled with the radiation that was emitted by the particle following the path associated with the spin up. And this component will be entangled with the radiation corresponding to the spin down. So the point is, if these two states are different, there will be some decoherence between the two. So if there was no radiation emitted and this was vacuum and this was vacuum, then these two things just add up and you'd get the spin X that you started with. But if these two, on the other hand, if these two things were orthogonal, these two components would be completely decohered. So the decoherence is actually determined by how orthogonal these radiation states are. So, and the decoherence that I talked about in the original Gedanken experiment is a result of these states not being the same, and well, they won't typically be anywhere close to completely orthogonal. They'll still have a big vacuum component, but nevertheless, this is not one, and there will be some decoherence. Okay, but now in the black hole case, everything I just said, now doing this Gedanken experiment with a black hole around, everything is the same with one more twist to it, which is the radiation doesn't have to all go to infinity. Some of it can go into the black hole. So the radiation state, in fact, is some state corresponding to radiation at infinity and producted with some state corresponding to radiation that goes in the black hole. Okay, so it's now the orthogonality of this joint state of radiation going to infinity and radiation going into the black hole in path 1 versus path 2, that's going to be responsible for the decoherence. Now, if Alice does everything sufficiently slowly, she can, arbitrarily come arbitrarily close to emitting no radiation to infinity. This state can be arbitrarily close to the vacuum, as would that, in which case they're going to be essentially the same state, and the magnitude of their inner product would be 1. So if there weren't a black hole around, she can keep her superposition perfectly coherent. I mean, of course, she has to avoid all other sources of environmental decoherence, but I'm not interested in that in this talk. I'm only interested in the kind of fundamental decoherence due to radiation. But she can avoid that in flat space, and with the black hole around, she can similarly avoid having any decoherence due to radiation from infinity. But what I'm going to show you is she can't avoid having the radiation that goes into the black hole be very small. And in particular, she can't, it doesn't matter how slowly she does the recombination. If she keeps her superposition open for a long enough time, she has no possibility of making this large. And in other words, she has no possible way of avoiding the decoherence of her particle. Okay, so to understand that, we need to understand what's going on with electromagnetic radiation through the horizon. And we need to understand that, well, first at the classical level, and then we need to understand it at the quantum level, of course, to see how much decoherence that results in. So the radiation through the horizon is completely described by, well, what I'm calling the electric field at the horizon. Usually you define the electric field with the field tensor dotted into a time-like vector. I'm defining it by dotting the field tensor into the null normal to the horizon. And this electric field will only have angular components on the horizon. And if this is zero, that is saying that there's no radiation through the horizon. And indeed, if you have, let's just for simplicity consider the field of some static point charge outside the black hole. It's not hard to show that indeed the angular components of the electric field on the horizon will vanish. They really have to. The point charge should not, sitting there in a static configuration, should not be radiating through the horizon. But there will be a radial component of the electric field on the horizon. And, well, you'd expect that from the Coulomb field of this static charge. And really, this is just saying that the Coulomb field perfectly well penetrates into the black hole, which it does, and that's actually critical. Okay, but now I'm going to consider the very simple situation where we have a point charge, initially static, and now I just take that point charge that's located over here outside the black hole, and I move it to some other location like here outside the black hole, and then I hold it in this new location forever. So, of course, there'll be some radiation when I move the point charge. And in fact, you can, well, see that from the, divergence of E equals 0, or divergence of F equals 0 Maxwell equation, which will tell you in this case that the angular divergence of this angular electric field has to equal the time derivative of this radial electric field. I mean, we have time and r here rather than radial divergence or something because of the way I've defined the electric field and its radial component with these null vectors. So the radial electric field, of course, is going to change because I've changed the location of the particle, and that implies that the angular components can't be 0. But it implies something much stronger that has the major implications for everything else I'm going to be saying in this talk, which is if I take the time integral of the divergence of the electric field, I'm going to get the difference of the radial fields between the initial and final positions. And those are different. So that's saying that not only is the angular components of the electric field different, non-zero, I'm sorry, while I'm moving the charge, but its integral is non-zero. Its time integral is non-zero. Okay, so what does that have to do with anything, and why am I making a fuss about it? Well, if we were interested in how much energy is radiated into the black hole, that's given by the square of the electric field. And I can make this arbitrarily small by moving the charge slowly. And, in the process, Alice's process, I can completely neglect any radiated energy that goes into the horizon. But what we're really interested in is how many photons are radiated into the horizon. And I'm about to show you that the fact that this is non-zero means that, in fact, an infinite number of photons are going to be radiated into the black hole. If that sounds completely crazy and shocking, I'll give you a little hint that this is exactly the same phenomena as occurs in infrared divergences in quantum field theory when considering scattering phenomena in 4 dimensions. But this is now for the black hole, and actually this would hold in any dimensions with the black hole. So to understand the number of photons, we have to understand what the quantum state of the electromagnetic field is around the black hole, both before and after we perturb it with the point charge. And for a black hole formed by gravitational collapse, the state should be very accurately described by the Unruh vacuum. That is the state that you should get when the black hole has settled down to stationarity, which it would do very quickly. The Unruh vacuum has, the Hawking radiation in it. It's the precise state that would describe what the Hawking radiation would be. Now, it's more convenient to work with the so-called Hartle-Hawking vacuum, which would correspond to a black hole that is in thermal equilibrium. If you imagine the black hole were put in some box and came to thermal equilibrium with the radiation in the box, that would be the Hartle-Hawking vacuum state at low frequencies near the horizon. These are essentially indistinguishable, so I'm going to work with the Hartle-Hawking vacuum. So when we're interested in the coming with the Hartle-Hawking vacuum is a notion of photons at the horizon. The Hartle-Hawking vacuum is the vacuum of a Fock space of the quantum field. And the notion, if we look at what does a one particle state correspond to, it'll correspond to a solution that's purely positive frequency with respect to affine parameter at the horizon. Okay, so what does that have to do with anything? Well, each component of Alice's particle is going to radiate into the black hole is, at the quantum level, a coherent state associated with the classical retarded solution associated with the charge current source provided by each component of Alice's particle. So that gives rise to the following formula for the number of photons that a given component of Alice's particle will radiate into the horizon. Or we can forget about Alice and go back to my point charge example. And what this is saying is if I want to know how many photons are radiated into the horizon when I move the point charge from here to over there and leave it there forever, I calculate the vector potential at the horizon associated with this by looking at the retarded solution. I Fourier transform it on the horizon. I take its positive frequency part. That's why I'm integrating only from 0 to infinity. I take its positive frequency part with respect to affine parameter on the horizon. And then I take this integral, which would be, I think, to many people or people who've studied Klein-Gordon quantum field theory, easily recognizable as the Klein-Gordon norm of this mode function. This extra omega factor comes in the integral of the amplitude squared in Fourier space of the radiation. So this is the number of photons that gets radiated into the horizon. But now we have a situation where the integral of the electric field is not, the angular components of the electric field is non-zero. That means that if we integrate this, the vector potential has a step function kind of behavior, the angular component. So I think I have a diagram on the next slide, so let me jump ahead to that if I can. Yeah, so this is what the vector potential must look like in this process where, let's say, I take a point charge that initially was here, and by gauge, I can assume the vector potential is 0. The angular components of the vector potential are 0 here. In the process of moving it, the angular components will be non-zero, but when I leave it in its final position, the radiation will be 0. There'll be no time derivative of this. So the electric field will go back to 0, but the vector potential won't go back to 0. But the instructions for calculating the number of photons are to Fourier transform this. When I Fourier transform this, I'm going to get a 1 over omega divergence. That's just what you get with a Fourier transform of any step function that, with a non-zero step. So let me jump back to my previous slide. This is the integral that we're supposed to take, but this Fourier transform diverges like 1 over omega. I have to square that. That gets multiplied by omega. If I was doing energy, that would get multiplied by omega squared, and I'd get a perfectly finite integral that I could make very small. But with only 1 power of omega here, I get a logarithmic divergence. And so if I did my point charge experiment, held it here, moved it over here, and held it there forever, I will radiate an infinite number of photons into the black hole. And as I've already said, this is exactly what happens when you do scattering theory calculations and calculate the photon radiation. There, it's a change in momentum that results in this kind of infrared divergence. Here, it's a change in position that will result in this kind of infrared divergence. Okay, so well, we're going to get back to Alice's experiment and see how much decoherence there is, but it will be important for making estimates to see if I have this point charge example, how large this step is in the vector potential between its initial value and its final value. And that can easily be estimated from Coulomb's law. If your point charge is some distance b away from the horizon, the radial electric field will be roughly charge of the particle over distance squared. That is just Coulomb's law. The change in electric field caused by moving in radial electric field caused by moving the charge a tiny little distance d will be given by this sort of dipole formula. And when you go through how much of a change in the vector potential that corresponds to, well, you have this dipole and distance cubed coming in from here, and then there's a factor of m squared that you'll also get from the volume element that comes in the Klein-Gordon inner product, given that the radius of the horizon is of order n. Okay, so now let's go back to Alice's experiment and see how much decoherence there is. And the point, each component of Alice's particle is like this point charge that gets moved, held in position, but it's not held in that position forever. It's moved back to its original position. That's what happens when Alice is closing her superposition. So each particle is, each component of her superposition is doing that. And that gives rise to this, well, if her superposition was held open forever, that would give that logarithmic divergence, and I'd get infinity here. But if she's only holding the superposition open for an affine time v, there'll be a logarithmic term, log of v, coming in here. Now, if the effect were just logarithmic in time, that you'd really have to wait a long time for there to be a big effect. But there is an exponential relation between affine time at the horizon and time in Alice's lab. So this logarithmic effect actually turns into a linear in time effect. So what I'm saying is that in Alice's experiment, this is how many photons she will necessarily, I mean, she could emit a lot more than this by doing her experiments sloppily, but no matter how carefully she does it, the infrared photons that are going to go into the black hole will, in number, correspond to this that linearly grows with time. Now, by the time that more than one photon has been emitted, the two states that you get will be orthogonal or nearly orthogonal, and complete decoherence will occur. So we're now ready to give the answer to Alice's experiment. So now in her experiment, she's put her particle in this spatial superposition. She keeps the particle superposed for a time capital T, and then recombines the particle. And what's relevant is this number of what you might call entangling soft photons that controls the orthogonality of the two radiation states. By the time this is bigger than 1, will have complete decoherence. So if you turn around the formula, it says that if Alice holds her superposition open for a time equal to the 6th power of her distance from the black hole, the 3rd power of the mass of the black hole, and the kind of effective dipole moment she's created with this superposition squared. These are all in units where G, C, and H bar are equal to 1. By this time, if she waits this long, her particle will be completely decohered due to the black hole. So I've written this in units where G, H bar, and C are 1. That might be useful to convert this back to more normal units, and might be useful to see what the size of this effect is in an example. And I've given an example here, and all the experimentalists can breathe a sigh of relief that they don't have to worry about this effect in their own laboratories, because the example I've given is, suppose that our sun were a black hole, and Alice's lab was at a distance of this black hole that the Earth is from the sun, so that's really quite far away from the black hole. And suppose that she had her superposition was actually made out of an electron. I mean, you do better with a nanoparticle, but let's imagine that it was an electron and she separated it by a meter. That's pretty generous and not that easy to maintain a superposition of that sort, but let's suppose she did it. Then the black hole at the position of the sun would decohere her superposition in a mere 10 to the 43 years. Okay, but if you were really close to the black hole, say corresponding to, at a distance corresponding to last stable circular orbit, that's awfully close, then you're really talking at same other parameters, then this would be a decoherence time that would only last 5 minutes. So this particle would be decohered in only 5 minutes. Again, separating an electron by a meter for 5 minutes in anyone's lab would be a very, very tall order due to all the other environmental effects. Okay, so I've been talking about the electromagnetic case. I think let me just very briefly mention the differences. There's one major subtle difference in the gravitational case. Otherwise, everything really works in amazingly good parallel. So let's say that Alice does her experiment just with massive particles. She can't really avoid doing that anyway. And Bob is going to, in the original experiment, Bob is going to measure the Newtonian-like gravitational effects to get which path information. That would be the analog of measuring the Coulomb field that I was talking about in the original experiment. Okay, well, the analysis, and now we want to do the black hole version of that. The analysis follows by incredibly close parallel where one uses the electric components of the Wald tensor rather than the electric field, and compares that with the radial component of the Wald tensor instead of the radial component of the electric field. And instead of using the divergence of electric field equals zero equation as in electromagnetism, which is the constraint equation that you have in electromagnetic theory, we use the Bianchi identities in the gravitational case, and the Bianchi identities on the Wald tensor, when the vacuum field equations hold, are given by these formulas here. And if you put it together, you have the same equation you had in the electromagnetic case, except you have two indices and you have a double divergence and you have a second time derivative coming in. But you also have a second time derivative coming in the relation between the Wald tensor and the metric perturbation. And the upshot is that you have exactly the same, well, memory effect. I think I didn't use that term. I should have, but the fact that the vector potential doesn't go back to its original value is precisely corresponds to what is called the memory effect at null infinity. And so you're getting exactly the same sort of memory effect on the horizon of the black hole. And in the gravitational case, this corresponding effect is called a memory effect. There is one difference that occurs in the gravitational case, which is that you might think that Bob could measure the difference in Newtonian fields, that would also be a dipole effect. But in the gravitational case, there is an effective conservation of center of mass law, which implies that if Alice creates a little dipole with her particles, her lab will actually move in such a way as to cancel that dipole. In a sense, this is exactly the reason why gravitational radiation starts at quadrupole rather than dipole in the non-relativistic motion kind of case. So what turns out to be relevant is the effective mass quadrupole that's produced by her superposition. Otherwise, if you carry things through in complete parallel, you get this formula for the amount of time it would take to decohere Alice's superposition. So you have a higher power of the distance from the black hole, which is really coming from this quadrupole rather than dipole effect, and you have this effective quadrupole squared here instead of effective dipole, and you have a correspondingly higher power of mass of the black hole. If you put in the estimates for what this is, well, in my example here, you get a decoherence time of 10 microseconds. That is really fast. And, that is making it sound like this gravitational effect is big. But this is the decoherence time. Again, if our sun were a black hole and we were a distance from the black hole that the Earth is from the sun. But now I'm doing the example of you take the entire Earth and put it in a superposition with itself, separated by an Earth radius. So that is, to say the least, a rather tall experimental order. But if you could manage to put the Earth in a coherent superposition with itself, separated by an Earth radius, and the sun were a black hole, it would decohere that superposition in just 10 microseconds. But for anything realistic, the decoherence time is way longer than in the electromagnetic case. Okay, a final comment that I want to make is that really the only thing that was used about having a black hole is having a killing horizon present. And that means that everything I've said in the talk having to do with black holes can be immediately generalized to an accelerating lab, and where you have this Rindler horizon. If you have a uniformly accelerating lab, again, spatial superpositions will decohere with formulas that are direct analogs of what I derived. And in the case of de Sitter space-time, where you have a cosmological horizon that's a killing horizon, again, the same analysis occurs. So in the de Sitter case, in the electromagnetic case, you get a decoherence time equal to the cube of the Hubble radius divided by the dipole squared, again in units where G, C, and H bar are 1. Well, the G isn't relevant for this formula, but the H bar and C are 1. And again, in the gravitational case, you get a higher power of the effective distance to the killing horizon, and you get the quadrupole coming in squared rather than the dipole squared. Okay, so what have I told you? I mean, just to wrap up and conclude. So what I've shown here or attempted to show in this talk is that black holes, and as I just said, much more generally, killing horizons, manage to harvest information about quantum superpositions of spatially separated components. So that's what I meant in my subtitle at the very beginning of Black Holes Are Watching You. They are gathering information about your quantum superpositions and figuring out which path your particle is actually in effectively. The mechanism by which they do this is absorbing radiation, but the relevant radiation and the thing that you can't do anything about is this soft radiation, the same type of phenomena associated with infrared divergences. So the long-range fields penetrate into the black hole and they change the state of the field, on the horizon, in this kind of soft graviton or soft photon manner. And that's how the black holes get the information about your superposition. And if you wait long enough, even though you're not doing anything and you're just holding your superposition open, the black hole will harvest enough information to decohere your superposition. So I think I've also illustrated with my numerical examples that this is certainly not going to be of any practical importance for any experiment that anyone might even contemplate trying to do. But I think it may be giving us hints of some significance for our understanding of the nature of black holes and quantum gravity. Okay, so thank you very much.
Thank you very much, Professor Wald. So now the session is open for a few questions. Possibly I will kickstart the question session. So that was a very exciting talk. Now, is an analog whether this calculations can be done for acoustic black holes, where because of finite velocity of sound, you have an effective horizon. So many of the conclusions that you have, can it be tested in acoustic black holes in the lab?
Yeah, actually, I haven't thought of that, but certainly off the top of my head, everything, including, the kind of radiation and so on, would in principle, apply to the acoustic black holes. But I mean, the trouble is the models and certainly the kinds of things you could do in the lab are typically only good models of the black hole in some limited frequency range. I mean, obviously any of the condensed matter things certainly wouldn't be very good at very high frequencies. That's no problem because the high frequencies are not relevant here. But they would have to be a very good model of the black hole at extremely low frequencies as well. So I think one would have to look at things on a case-by-case basis to see that we're talking about radiation that is extremely low frequency, and it's really and I guess we really need an analog of a Coulomb field or Newtonian field of the thing that we're putting into superposition, and something of that sort that would go through the black hole horizon. So, I mean, in principle, if one had like Bill Unruh's original, model was sound waves in a fluid. If you just had a fluid with the sound waves and everything worked at all frequencies and so on, and I guess you also need, when you're making the superposition, that there's some analog of a Coulomb field that might be an issue with the sound waves. But anyway, that almost everything and possibly everything would carry over. But, the fluid, a laboratory fluid is not going to behave like the fluids in the model is probably not going to behave that way at incredibly low frequencies. And of course, probably even the more major showstopper in terms of some experimental verification of this is, I've assumed that there is absolutely no environmental decoherence from other causes. But in these condensed matter models, I mean, avoiding environmental decoherence and then seeing this really subtle, very low frequency effect, I think is probably not going to end up, being close to something feasible to do. But that would be interesting to think about further and see what elements would in principle work.
Thank you, Professor Wald. Professor Panchapakeshan has a question.
Yeah.
Yeah, Professor
Hello, by
Panchapakeshan.
the way. Oh, you're muted.
I think Professor Panchapakeshan, you're muted. Professor Panchapukeshan, you must unmute.
Okay, I just wanted to ask whether these arguments have any relevance for the information loss when Hawking radiation makes the black hole disappear.
Yeah, not really. I mean, if anything, they make the information loss issue, more difficult to overcome, because now one can see that there's a lot of, soft information that the black hole absorbs as well. But I mean, one might be tempted to think that this might help because the Hawking, Perry, Strominger ideas were somehow related to, soft radiation and soft hair they talked about. But, in what we're talking about, there's no sort of soft hair on the black hole that you can, go to later and pick up the information about what went in. Everything is really going into the black hole. So if anything, it's making the information problem worse. But, if you can solve the information problem, before what we said, this will only add an extra complication. But I don't see that this helps provide a solution in any way.
Thank you.
So Professor Rao has asked a question. Let me read out the question. So the question says, the spin degree of freedom has nothing to do with charge and does not reside in 3D space. Thus, what Alice does with Stern Gerlach in Z direction on an initial X state and then takes it away should not affect any Coulomb effect of that particle on Bob.
Okay, so
yeah.
Okay, so I had spin. Let me see if I can get back. Yeah, I gave Alice's particle spin, and I assume that just in order, the spin is playing absolutely no role in this. But with the spin, I have an sort of straightforward mechanism for separating things into a spatial superposition with a Stern Gerlach apparatus. But more importantly, it's a very clean situation when I bring the particles back together. I can just ask, does the spin go back to the X direction, or is there some possibility that it might be in the minus X direction? And that's a clear criteria for whether there's no decoherence or some decoherence. I could just as well not have the spin separated into these superpositions and then do some kind of interference experiment and see whether I get a wiggly pattern on the screen or the non-wiggly pattern that you'd get if these were decohered. I wanted to avoid doing that because there are previous papers in the literature doing talking and not talking specifically about this Gedanken experiment, but that make some arguments about not there being some Planck scale limits, or Planck length limits, imposed on the interference pattern due to quantum gravity effects and so on. And so I wanted to avoid having to do an interference experiment. And if we do the spins, we can avoid that cleanly. But otherwise, the spins are playing no essential role here. So I'm not sure if that fully answered the question, but the spins are completely inessential in this discussion. We just have to work harder to figure out how to make the superposition and work harder to figure out if it remained coherent.
Just to add a comment, since every particle has mass, one can just take the gravitational waves going into the horizon of the black hole and check the decoherence.
Well, the particles that we're talking about, I mean, in Alice's experiment with the black hole, the particles are never going into the black hole. It's only the gravitational radiation that goes into the black hole. The gravitational radiation due to the particles traveling these different paths.
And circumvents having charged particle, since everything has a mass, even superposition of just normal magnetic moments without any charge, but the gravitational waves going in would cause the decoherence.
Yeah, everything will in fact decohere, but if I mean, even interaction, even massive fields, will have some radiation going into the black hole. They'll just be much smaller. I mean, so, if we did this with magnetic moments or something instead of charges, and again neglected the mass, we'd still get some electromagnetic effect. It would just be much smaller, and now we'd have to be looking at the difference of the radiation from the different magnetic dipole moments. But everything will have mass, so in the gravitational case, the analysis that I described would apply to everything. But in the electromagnetic case, I mean, we could do this with neutrons, and there still would be an effect because they have a magnetic dipole moment, and they would radiate differently, but it would just be a very tiny effect compared to what you'd get with charge. But the linearly growing in time would apply to everything.
Thank you. I think there's the last question from Professor Hegde. He asks, if black hole can decohere any quantum superposition, is there any rate at which it decoheres, or does it depend on any other factors?
Professor, I apologize, folks. Professor Patrick Dasgupta, Arnav has been asking questions. He was in fact first in queue. So maybe if you could, his question could also be taken up, please.
Sure. Yeah, absolutely. Yeah, after this question. Yeah.
Thank you.
Okay, sorry. The question was, what is the rate of decoherence? Well, I gave a decoherence time here. This is the time at which nearly complete decoherence would occur, but it is the decoherence rate, is exactly what's given by this, one over this decoherence time is essentially giving you the decoherence rate. So this is in the electromagnetic case, and the corresponding formula in the gravitational case is this. So if you just take 1 over this, that would be the decoherence rate.
All right, thank you. Question by Mr. Arnab Barbad. It says that in one of the slides, it was assumed in the calculation that superposition stays forever. What if experimenter opens a special superposition, then recombines them before any soft particles can reach any horizon?
Well, I mean, right, when, this is the vector potential that's associated with creating the superposition and bringing the superposition back to zero. So if we hold it open for a very long amount of time, the frequencies will be 1 over the time we're doing it. I mean, I should really distinguish, between the affine time and the killing time or the proper time in Alice's lab, but the idea is still basically the same. So, there isn't an infrared divergence in the actual experiment because we're bringing this back to zero, but 1 over the time, that I'm keeping it open is the important frequency that comes in, in creating this infrared divergence. So if we do the superposition very quickly, then we're not going to, I mean, it's not a question of how quickly we bring it back together and how quickly we open it. It's how long we leave it open that is what's most relevant. If we don't leave it open for a long time, then we don't get a big effect in this manner, though, of course, we'll still get some radiation from the opening and the closing, and we'll still get a little bit of decoherence, but that can be way smaller than what I was calculating here. So I think that was addressing the question, but.
The second question that Arnab asks is, does it mean no long-term quantum computer would ever be stable because of this decoherence?
Oh, yeah, but we're talking, I mean, yes, but I don't know that anyone is thinking about a quantum computer that's stable for 10 to the 43 years. And we don't actually have any black hole as close to us as the sun, and we don't have to do something as challenging in a quantum computer as keeping an electron in a spatial superposition separated by a meter. So, you can do way better than the 10 to the 43 years due to this effect. And again, I don't think anyone building a quantum computer is looking for it to work coherently on that sort of time scale.
Thank you. So all the questioners have also thanked you in the chat box. Are there any more questions? Well, there doesn't seem to be any other question. So wonderful. I really thank you, Professor Wald, to have delivered such an exciting lecture, and it has raised a lot of questions. And on behalf of everyone, I thank you very much.
Yeah, okay. Well, I enjoyed being here, and thank you.
Great. So with your permission, Professor Patrick Dasgupta, may I request Professor Haridas to give a vote of thanks and to conclude this two-day lecture series in the memory of Professor Ashok Nath Mitra, please.
Professor Haridas, you're muted. You have to unmute yourself.
Well, on behalf of the Mitra Memorial Lectures, we first of all wish to thank both the speakers for very exciting and thought-provoking and radical presentations about what is clearly the frontier of one of the frontiers of physics. And I also wish to thank Patrick Dasgupta and Alok for co-chairing the two sessions. And with that, I ask Alok to say a few concluding words. Thank you.
Great. So my one paisa worth of concluding remarks. So thank you, Professor Wald. And of course, Professor Hooft has logged out. And Professor Andrew Linde in the morning, speakers for today. And all the few body physics session speakers yesterday. And Professor Indranil Mazumdar for arranging that few body physics session. Thank you so much. And of course, Professor Pramnath and Professor Amitabh Roy Chaudhary also for chairing that session. And Professor Mohammed Sami for chairing today's session, Andrew Linde's talk, and of course, Professor Haridas for looking after this this mega post-lunch session. Thank you. We had some hiccups connectivity-wise, but okay, that is unfortunate. Professor Hooft was facing some connectivity issues, but I think once the talk got started, it was not interrupted. Thank God for that. And I'm not very good at thanking people. I think we know what we have done. So I think now I know if I ask Dr. Gargi Mitra, who is online, she's the only surviving member of Professor Mitra's family, to say a few words. She's going to say no, so I'm not going to do that. So save everybody the bother. And now with Professor Haridas's permission, I'd like to actually ask one of the architects of the website, Shivam Singh Aswal, to unmute and turn on the video so that we can have a look at who you are. Is he around? Are we seeing him? Okay.
Yeah, I'm just give me a minute.
We don't have a minute, man.
Sure.
You would know more. There we go. That's
Hello,
Shivam.
everybody.
So he's our alum. He was he passed out last year. Yes, was it last year? Yeah. And now he's into Texas Instruments for reasons best known to him. So, but anyways, we are hoping maybe he can find his way back to physics sooner than later. So thanks, Shivam. And he was also very ably supported by Rajneesh Kumar Jha, who is currently a grad student at the International Center for Theoretical Sciences at Bangalore, and Ayush Ashray Anand, who is also an alum. So these three are the trio, the integrated master's MSc batch. And then let me also ask Rupa Pramodan, who is the current BS MS 50th year student, to please turn on your camera so that we can have a look at you, who you are. And thank you so much for designing the poster for this series on very short notice. I think she did it in like 3 days, maybe 2.5, if maybe even that would be probably an overestimate. And she's been sitting here in my office, man, since yesterday, 2 p.m. IST, right through all the lectures. bearing with my stupidities and so forth and so forth. God bless all. And I think I have covered all bases. I guess if I've left unaddressed, I'm sorry. One more thing, I don't know, this is not really appropriate, but I really cannot, I would succumb to this temptation. I also like to thank my wife, Anamika. She's actually sitting right next to me. She's looking after feeding us. So she's been feeding Rupa and me with all sorts of goodies. As I mean, you got to bribe folks, right? So I mean, that was the bribe. The food was a bribe. I'm just kidding. I'm just kidding. So, anyways, I mean, it was kind of a family affair for us here back home, and I'm sure everybody. And thank you, Professor Patrick Dasgupta. You've been such a source, especially for advice, I openly admit. Thank you. And
Thanks, Alok. Yeah.
with that,
Wonderful.
folks, I think thank you. And God willing, we might meet the other side of 26 and 27. So till then, namaskar. Bye-bye. Take care. Stay safe. Crazy times.
Okay, bye.
Bye, Professor Wald. Lovely seeing you for such a long time. Thank you.
Yeah.
Bye-bye.
Bye.
Okay, so I think we can end the meeting, folks, right? Yeah.